Ma'am, shall we start the session, ma'am?
Yes, ma'am, proceed.
This session will be handling by Mr. Deepak Yadav. Deepak Yadav is currently working as a data scientist in ABB Global Industries and Services Private Limited, ABB Ability Innovation Center, Boruka Tech Park, Whitefield, Bangalore. He is having 3 years of experience in this company. He is a postgraduate in the field of data science and has a strong mathematical background. His areas of interest are statistics, predictive maintenance, text analytics, Docker, and cloud computing. Now he is going to deliver a lecture on probability and statistics for data science. We welcome you, sir.
Hi everyone, very good morning. Thanks for the quick introduction. I hope you can hear me.
Yes, Deepak, you can proceed.
Yes. So I hope everyone is keeping yourself safe, fit and fine. Yes, so let me just quickly present my screen. Just let me know when you guys can see it. So is it visible?
Yes, it's visible.
Okay. Yeah, so today I have chosen the topic probability and statistics for data science. As you can see, this data science, it is made up of two words, data and science. But when we see those two, words separately, data and science, so they have their own meaning. Data has its own meaning, science has its own meaning. But when we club both the things together, obviously the data gets power. So what do I mean? The data gets power. So let's assume we have around 80 people present in the workshop. When I say 80 people, yeah, it gets some amount of information. But when we deep down, when we drill down the other informations, like, okay, what kind of people, whether they are from the CSA department, are they from the EC department, or are there any statistician, mathematician, what are their area of interest? And if you can get those kind of insights from the data, then obviously people will be interesting, our customers or anything, people will be interesting about the facts. And that's what we do. So data alone is not interesting, but when we put some kind of science behind it and we interpret our results, obviously the amount of information we get, they are pretty interesting. So the science I was talking about is nothing but the statistics, because this is where everything starts. Whether you consider about a simple line chart or your deep learning algorithms or your reinforcement learning stuff, or just consider a self-driving vehicle, but recently Tesla is also driving. So this is the place, we do all these deep down algorithms, but eventually it's all starts from the data science or statistics. So that's why I chosen this topic, and I guess rest of the 3 days of the workshop, people will be talking about other concepts like deep learning and reinforcement. I think this particular introductory session can help you guys just to brush up your concepts of probability and statistics. So yeah, let's get started. And yeah, you can ask any questions in between. You can put them in the chat. Maybe I can take up in the last or in between in the slides. If I get some time, I will try to take the questions. So please feel free to do that. So this is the agenda of our talk. I have separated two things, probability and statistics. And probability starts with random variables, PDF, CDF, different kind of distribution I will be covering. And there will be conditional probability, Bayes theorem. And when it comes to statistics, I have taken the descriptive statistics like mean, median, mode. Everyone must be familiar about it. Bose-Wixer plot, covariance, correlation, moving average, and I'll try to finish it with the hypothesis testing. Yeah, so what is probability? Obviously, it's everywhere. Whenever you consider anything, like whether it's going to rain, it's probability. Because whenever we are not consider about any certain situations, it's all about probability. Let's consider, how many people are going to join this workshop, maybe 100 or 150. But if we know the number in prior, obviously we can make our own arrangement. At least our IT team can make some arrangement. If 1,000 people are going to join the workshop, they might have switched to Zoom video call or some other platforms where the buffering won't be there. So if we know something in prior, obviously we can make better decisions out of it. That's where the probability comes into the picture. And these cards, dice, and all those examples we have seen throughout our life, our 10th standard, 12th standard. So those are the basic stuff. But eventually now it's all about getting something in prior. And that's what the data science field is all about. We are just doing the prediction part. And that's where people are happy about it. Let's consider the weather example. If we say today evening it's going to rain, if you are very much accurate about it, obviously people are going to like it. And that's what the data science is. Let's consider the predictive maintenance thing. If we know a machine is going to break down, the operators can plan for the maintenance in prior, so that it can save a lot of production issues, a lot of money can be saved. So that's what the data science is all about. Everyone here is talking about anything in prior or anything in advance. So that's where the probability is, and that's the backbone of data science. So we have some common terminologies like, okay, what kind of data we are talking about, what is random variables, and different kind of probability functions. So the data basically we categorize into two parts. One is a discrete one, another one is the continuous one. So discrete is like we can count those things, rolling a die. We know that it will be 1 to 6, and those are the countable numbers. And then tossing a coin, there will be only two outputs, head and tail. So those are the discrete numbers. But when it comes to continuous data, there will be plenty number of options available, like height. There will be height in feet, and then in the decimal points, and anything which is very very which cannot be represented or which cannot be countable. Those are the continuous numbers, continuous data. But whenever we see any data set in our day-to-day life, those will be mix up of discrete and continuous. So that's the place where we have to play around. And then we have something called random variables. So random variables is nothing but the output of one of the experiment. The experiment can be anything. It can be a cricket match. What is the output? Either it will be a win or it can be a loss. So that will be our random variables. It can be a output of a coin. It can be head. It can be tail. It can be output of a die. I mean, any kind of experiment, if you consider the output of that experiment, this is called the random variables. Sometimes it's pretty confused, but the terms random is not very random, let's say in that way. And then we have different kind of probability functions. What these functions do, these functions basically help us to find out the different kind of probability distributions present in our experiments. So we have probability mass functions. So whenever we talk about the discrete data, so the discrete data is nothing but the rolling a die, coin, card. These are the discrete data. So whenever we have a discrete data, we always consider the probability mass functions. So this is nothing but, let's say, what is the probability of getting 1 in a die? So obviously it will be 1 by 6. That's what I'm talking about. So in terms of the mathematical stuff, we call it probability mass functions. Let's say the coin, obviously probability of getting head will be 1 by 2. So those comes under probability mass functions, as you can see the function here. So this x is nothing but the output of our experiment, and this is where the probability we are trying to finding out. Then we have something called probability density function. So whenever we tackle problems with the continuous variables, we consider probability density functions. Let's say the people right now present in the workshop, let's find out the age range. How many people are present with the age range of 30 to 40? Find out the probability of those people. So this is where the probability density functions comes into the picture. We always talk about the range. And then we have something called cumulative density function. So so it is nothing but the total probability of anything below it. Let's say the people who are present right now are age of 50, finding out the number of people who are below 50. So those kind of probability questions we tackle with the help of cumulative density functions. So this is nothing but similar to like we have the frequency and the cumulative frequency. The similar way we have the density function and the cumulative density function. Yeah, so just a second. So in another terms, let's say I want to get the probability of today's temperature, that will be around, that will be 45 degree. So if I'm talking about the specific number 45, I'm talking about the probability mass functions. That's where these functions will tackle the situation. Whenever we are very much specific about a number, but whenever we are considering a range, let's say the probability of temperature having around 45 to 50 degree, that's where the density function comes to the picture, because we are talking about a number of range. It can be 40, it can be 41, 41.1. So whenever we consider these kind of situations, we consider probability density function. And whenever we are very much specific about a number, it's always the probability mass function. So we don't use much in data science, but obviously whenever we receive a problem statement from anyone, those are the common terminology we receive, and we should understand about those things to get the better predictions or better outcomes from the data. And this is the graphical representation of all these three functions. As you can see, I was talking about probability mass functions in terms of discrete data. You can see the number 1, 3, 7, those are nothing but the discrete data. And if I do it from n number of times, I will see some sort of distribution of the data. And this is what we are doing here. Similarly, the probability density function, we are talking about a range. Let's say the temperature between 40 to 45, then we'll be having a range 40 and 45, what kind of the data presents. This is where the density functions comes here. And similarly, let's say the temperature will be below 45 degree. This is where the cumulative density function will come into the picture. And this is the area under the graph, will tell us the total CDF. So next, the distribution. I think this is one of the important topic, and whenever we receive any data set and we feed it to any kind of model, and this is the first step we do, we find out the distribution, how the data is distributed. And this is one of the most important step. I mean, there are multiple type of distributions available, but I will try to include Bernoulli, binomial, and normal, because those are the most important ones. There are others like uniform, Poisson, and exponential. They are little theoretical. We hardly use it in any of our modeling, but these are the three distributions we use it in a regular way. So what is Bernoulli distribution? Okay, let's talk about a cricket example. And we are playing a cricket match, and who is going to bat and ball? We are just going to decide based on the toss, and the toss will be whosoever is calling for head, he will win. Otherwise, the other person will lose the toss. So there will be only two outputs. Either it will be a head or it will be a tail. And we are only talking about a single trial. So whenever you see these kind of scenarios, like we have only two possible outcomes, 1 or 0, success or failure, head and tail, those kind of scenarios, and we only talk about a single trial. We do it only once, like a cricket match. We toss only for one time. This is nothing but a kind of Bernoulli distribution. So this is how we plot it. And in some scenarios, like head and tail, obviously we have the equal probability of getting the outcomes. Like there will be 50% of chance of getting head and 50% is tail. But there need not to be the equally likelihood of success and failure. So like say for example, a professional boxer is playing with a noob. So there are always a higher chance of winning from a professional side, because he is much experienced. So in that case, the probability of winning and lose is not equal, because the outputs are biased. And you can see in this particular scenario, the success rate is pretty less, but the failure rate is pretty high, because the distribution, the probabilities are not equally likely. We have some kind of bias available. So this is what the Bernoulli distribution is all about. So I mean, you guys can please stop me in between if I'm going too fast or I'm not audible or anything, any sort of thing. If you feel, please stop me at the particular moment. So now I'm moving to binomial. Yeah. So the difference between Bernoulli and binomial is the number of trials we do. So if experiment can be done in n number of times, we call it binomials. Obviously, the output will be 2. It will be yes or no, or success or failure. So in the similar cricket example, if I say if I toss, I'll get head, and then if I toss next time again, I'll get head or tail, anything. But remember that if I toss and if I win the match, or if I toss, if I choose to bet, that is totally independent of the tomorrow's result. If I toss tomorrow, it will be totally independent of today's situation. That's where, if those sorts of scenarios are considering, that's where the binomial distributions comes. So let's talk about the properties. Each trial is independent, as I said. If I toast today and if I toast tomorrow, there will be different. There will be two different scenarios, and those two are independent. There is no dependency between toasting today and toasting tomorrow. And obviously, there will be two possible outcomes. It can be success, failure, or anything. And we always go for n number of identical trials. And this is what the binomial distribution is all about. So when I say the probability of success and failure they are not equal, we might get some kind of skew distribution. It is more towards the left part. It may be towards the right part, because the probability of success and failure, they are not equal. But whenever we see the probability of success and failure, they both are equal, we see a perfect bell curve kind of a graph. It is a kind of a normally distributed data. Yeah, so this is binomial distribution. So whenever we plot anything, whenever we receive, say for example, a data set which is consist of 50 columns, like the features, we call it in our data science domain. So those features we try to plot. Okay, what kind of probability distribution it has. It is binomial, Bernoulli, or it is normal. And if we don't have those kind of perfect distribution, we try to make it perfect, and then we try to feed the data into the models so that we can get better results. So moving on to the next part. Okay, how we will get a Bernoulli distribution out of binomial? Any guesses? Yeah, so okay, it's okay. So as I told you, the Bernoulli distribution only talk about a single trial, but the binomial distributions always talk about the n number of trials. So if in this particular equation, if I put n is equals to 1, if I'm doing the trial only once, that will be nothing but a Bernoulli distribution. So they are somewhat correlated, they are almost similar, but whenever we do experiment n number of times, we consider that is a binomial distribution. If we do it only for once, it's a Bernoulli distribution. Moving on to the next, normal distribution or Gaussian distribution. This is one of the most important topic we do, or we always do whenever we try to model any data set. So in the normal distribution, what we assume, the mean, median, and mode, they all are staying in a similar point. As you can see, in the normal distribution, we find out that mean, median, and mode, they always stay in the center. And the total area under the curve will be total 1. And if you consider the half of the point, exactly the middle of the point, let me just open the pointer. Yeah, so if you consider this middle value, we will be having exactly half of the data in the left side and half of the data into the right side. This is what the normal distribution. If all these properties are satisfied, we call it as a normal distribution. So if you see this mean and variance, we find out the variance steps, say one standard deviation away towards the left and towards the right. We assume that there are around 60% of the data present. And if we say two points away standard deviation, like the mean minus 2 standard deviation and plus 2 standard deviation, we consider around 95.5% of the data will be lying. And if we see, there will be something called mu minus 3 sigma and mu plus 3 sigma. We are considering that approximately 99.7% of the data lying in this particular standard deviation. So what exactly these numbers are? So these are nothing but the standard deviation, how the data is distributed. So this is where this is what the standard deviation tells about how the data is distributed. So when we say the data from minus 3 sigma to plus sigma is containing almost 95% of our values, we call it, this is one of the property of normal distribution. But in normal day-to-day life, we don't receive this perfectly looking bell curve. Obviously, whenever you receive any problem statement or any data set, we hardly see any one of the columns or any one of the features in the shape of this particular thing, like the perfect bell shape, like the mean, median, and mode. They all are staying in a similar point. This is hardly we get. We expect that the data will be in this particular position or this particular shape, but we never get this. We will get this particular graph, like the right side skewed graph, or the left side skewed graph, because this is how the day-to-day process variation behaves. They cannot be normal. We have to convert into normal distribution. So what do we call it as a negative direction or the right skewed graph? So the median will be in the center, but the mode will be always greater than the median, and the mean will stay somewhere in the extreme left of the portion. So the condition is like mean will be lesser than the median and the mode. This is nothing but the rightly skewed normal distributed graph. In the similar way, we have the opposite, totally opposite, the left skewed graph. Again, we have the mode to be the lowest one, and then we have the median, and the mean will stay somewhere in the right portion. So that's where this is what is the rightly skewed distribution. And these are the day-to-day problems we face whenever we do any kind of modeling. It can be rightly skewed or leftly skewed, but we have to do some kind of changes. Maybe we can take log of the data so that the data can be converted into normal distributed plot, or we do some sort of different techniques are available to convert the data into normally distributed graph. So let's move to the next one. Okay, so I have just plotted the graph for the different three different standard deviation. So as you can see, if the standard deviation, I mean, if the variability of the data is very less, you can see the perfectly bell curved graph. But if the data is more spread out, if the data is having more variations into it, you can see the little wider graph. And if I say the standard deviation is 20, the data is having a lot of variations, obviously the normal distribution having a wider kurtosis. This is how we call it. And so this skewness and kurtosis. So kurtosis is nothing but the height of the graph. So here you can see it is having a perfectly bell shape, and it has a good amount of height in it. But the more is the variance, the more wider will be the plot. So this is just with respect to standard deviation. I just wanted to visualize how it behaves, the normal distribution with respect to standard deviation. We can plot n number of plots with respect to different standard deviation. You can see how the normal distribution behaves. So moving on to the next after this distribution part. Yeah, so G-score. So G-score is, we call it as a standard score also. You might have noticed somewhere in the problem statements like, okay, G-score, finding out this value and that. Whenever we consider normal distribution, this is one of the, the terminology we face, this G-score. So what exactly it is? It's always tells about how far one of the data point is from the mean. Okay, so let's say, someone weight is around 150 pounds. Obviously it's a sort of good information. We know the weight of a person, but yeah, what does it mean? If I want to compare that weight with the rest of the people, say for example, the workshop of, right now we have around 70 or 80 people. If I want to compare that particular weight with the other people or the mean of the population, what does that tell us? So this is where the G-score comes into the picture. Let's say this X value is nothing but the 150 pound, the weight of the people. And then this is what I'm talking about, the population. Let's say the people right now who are present in the workshop, the mean weight of all the people around 80. And then we have a standard deviation, how the data is deviated. I mean, whether the weights are almost similar or they are very much variated. If one person is having 50 kg or another is having 200 kg, or what kind of distributions we get. So once we put all these values, we will get a G-score. And obviously, if the G-score is positive, we will say the data is more towards the right of a mean. So right of the mean is nothing but, let's say this is the normally distributed graph. If you get a positive G-score, the data will be somewhere in the right portion. And if you get a negative G-score, obviously the data will be somewhere in the left side. Okay, so let's say the 150 weight I was talking about, and if the average weight, if the G-score comes out to be positive, we will say most of the people is having around average weight is 100, and the other people is getting 150. It may be an outlier also, and it may be part of the distribution as well. And if the data is somewhere presenting say 160 or 180, obviously that will be outlier. So those kind of basic descriptive stuff we can do with the help of G-score and normal distribution whenever we receive any kind of data sets. So I'm talking about the bigger amount of data set, because those things we cannot do manually. So we have to feed those sort of thing into one of the, the most popular programming language called Python, R, or MATLAB, wherever people feel comfortable. So it's always a good practice to find out all those things like the outliers and all those stuff that can be done using the normal distribution graph also, and the G-scores as well. Okay, so yeah, moving on to the next topic, conditional probability. Right now, this reinforcement learning is also very much, popular, and people are working into it. And so, when I was looking into that particular domain, so it's always starts with this kind of, statements. So conditional probabilities and stochastic processes and stuff like that. So I thought, okay, I'll include this topic also. Maybe it can help us in the reinforcement learning topics. So let's say, let's consider an example of airline prices. If we consider this, the airline prices throughout a year, obviously there will be a little spikes throughout the festive seasons. Let's say in India, there will be some kind of spikes available in the January month. And obviously during the Diwali month, we'll be having a huge spike in the data, and maybe during the Christmas as well. So if we know, and if we try to find out some outputs about the data, and if we know in the prior that, okay, these are the festive seasons in India, and obviously the price will go high, there will be there will be a sudden increase in the price. This is where the conditional probability comes into the picture. We know that there will be some festive, that's why the price were high, but we cannot consider it throughout the year. So that's where we talk about the conditional probability. We know something in prior, we want to find out what will be the output or what will be the outcomes of that particular event which is already occurred. So this is the conditional probability. And we call it, I mean, there are two famous keywords called mutually exclusive and independent events. They are pretty confusing terms, but they're nothing but the mutually exclusive thing is two events cannot happen together. Like tossing a coin, obviously there will be either head or either tail. Both the things cannot happen in the same time. Like either there will be head or tail. So there cannot be a midway. So that's where we call it a mutually exclusive events. So whenever we receive any kind of problem statement, we say, okay, the process is mutually exclusive. But we don't, I mean, we have to understand what exactly the mutually exclusive event is. And in the similar way, we have something called independent events. So independent, like the name itself is telling, there will be no independency. There will be no dependency. And like tossing a coin, sorry. Yeah, so tossing a coin, or say for example, you are tossing two different coins. So one getting head in one coin and getting tail in another coin, they both are totally independent. There is no dependency between, tossing these two coins. This is how the independent events are. And this is just a mathematical representation of it. If both the events are not dependent, like this is one of the basic conditions in the conditional probability, both the events should be dependent. That's how that's the only point we can find out some sort of information. If they both are independent, obviously there is no point of finding out the conditional probability, because that's what we say. If A has already occurred, what will be the probability of B? If they both are independent, if one person is going into the left, another is going to the right, there is no point of finding out the conditional probability. So as soon as they are dependent, then only we will get to know about the probability or the conditional probabilities. And these are nothing but the mathematical formulas. But yeah, based on this conditional probability, there is a famous theorem called Bayes theorem. And this Bayes theorem is backbone of the neo-Bayes algorithm. This is one of the classification algorithm in machine learning. So this is totally dependent on the Bayes theorem. So this is nothing but probability of A given that the B has already occurred. So this is how we're finding out. This is just a mathematical formula. But yeah, so if we consider this particular algorithm, this is very useful.
Professor, can I ask you a question?
Yeah, sure.
In this naive-Bayes theorem, actually this treats A and B both as independent, because naive, the name has been given as because they are initially they are thinking that A and B both are independent. Then if independent, then how this formula will be written like this?
So, I mean, you mean to say that both the things are independent? No, I don't think so. See, let's consider an example. I mean, if you see any kind of the data mining or machine learning books, there is a famous example given for naive-Bayes algorithm and the Bayes theorem. So let's say we are talking about the different conditions of weather, and then we are predicting the output whether we want to play or not. So if at all the conditions are out, I mean, the data is totally independent. Obviously, no algorithm in the world won't work, whether it is neo-Bayes or Bayes theorem or anything. As soon as the output variable have some kind of dependency with the input variables, that's the point where our any kind of algorithm will work. And the similar case is for the Bayes theorem, maybe the neo-Bayes algorithm. So as soon as the input values are dependent, at least one variable is dependent, that will contribute for the output. Otherwise, not. So that's the I mean, that's the bottom line. So I guess definitely there will be some kind of dependency available. If there is no dependency, obviously this formula won't work out. As I said in the previous slide, if there is no dependency, if they both are independent, the probability will be equal. So there need to be a dependency available. I mean, just for the neo-Bayes or any sort of algorithms. I mean, if whenever you feed a data set, just think about, we find out most of the time, we find out the correlation. And if there is no correlation at all in n number of features with respect to output, so obviously the model will not give us any result, any good amount of result.
Maybe we can apply this naive-Bayes theorem for more number of variables.
Yeah, obviously you can apply it for n number of variables. Say you have around a data set of
Because for two it is not, because for A and B maybe it is not applicable like this, because naive says that this we take variables as independent, and then this will be probability of A given B will be equal to simply probability A, because probability B get cancelled.
So what A and B here is, so A is, say for example, let's talk about the similar weather data. Let's say that today is sunny weather and the wind direction is this much and this and that, and then the output, the actual class is whether we want to play or not. Okay, this is A and B. So first we do what? We first of all we find out the probability of whether we want to play, and then we don't want to play. There are two categories. So we will check each and every features with respect to the class. We don't want to play, let's say, when weather is sunny. What will be the probability? If weather is cloudy, we don't want to play. If weather is, very humid and those kind of things. So we, at any moment of the time, this particular naive-Bayes algorithms, find out the probability between the output, the class, and one of the features. So at any moment, there will be two variables present. So I'm not talking about there will be only two variables present in the data set. There will be a number of variables present. There might be 5, 6, and there will be a class. But any moment of the time, we are finding out with respect to each and every variable and the class, the output. And this is how the internally algorithm works. We don't need to do manually. Obviously, when we have n number of classes present, there are, the data is not by classification, like the classes are more like 4 classes and 5 classes. This is how the algorithm finding out with respect to each and every class. It finding out the probability of each feature, and then we've come up with the best pair of weights. Okay, let's say the weather is sunny, the wind direction is the wind is also less, and let's consider it's a holiday for the students. Obviously people will go out and play. So those kind of best scenarios we're finding out for the classification algorithm.
Right.
Yeah, so this is what the naive-Bayes and so-called the Bayes theorem is. Yeah, so coming to that, I think I have covered the probability topic from my side. If you have any questions about the probability topics, please go ahead. Otherwise, I will stick to the statistics. Obviously, there are other topics which I haven't included, like Markov chain. This is one of the important topic for reinforcement learning problems. But when I was about to touch the Markov chain, it has another depth into it. It will take another half an hour to understand the Markov chain. So I just skip for it. But obviously, you guys can read about it, and it is one of the important topic for reinforcement learning. So if there is no question, I'll just move it to the statistics portion. Yeah, so when it comes to statistics, obviously it has two different parts of it. One is so-called descriptive statistics, another is so-called inferential statistics. So descriptive, as the name itself is telling, I mean, it describes the data, like, okay, what is the mean, mode, how the data is spreading out, what kind of variation it has, we plot the charts, we graph. So all those kinds of topics comes under the descriptive statistics portion. And when we say inferential statistics, obviously we do some sort of decision making in this particular portion. Like whenever we have two different things called population and sample. So whenever we perform any sort of algorithms, we always take some kind of samples out of it, we do the testing, and then we apply it throughout the population. So choosing out the sample is also one of the tasks. So this is another domain of theory of sampling in statistics. But in overall terms, let's consider the real life example of this corona vaccine. So obviously, I mean directly, whenever the people whosoever has developed the vaccine, they cannot go and apply it to the whole population because it's a kind of impossible task. So first, they have to choose some kind of samples. So the sample needs to be good enough. First of all, the size, and they should have enough kind of variations. Like the people should have different disease, and if it is working for each and every people in the sample, obviously they can do some kind of prediction for the whole population. So the choosing of the sample, what kind of variation it should have, if we have different kind of disease and all those things are there in the sampling method, and if our vaccine is working, obviously we can do some kind of inference and the prediction, like okay, obviously it will work for the most of the people present in the population. So this is how the sampling and population works in statistics domain. And inferential statistics we call hypothesis testing, confidential interval, linear regression. All those are part of inferential statistics. So I will try to cover both the things, descriptive and inferential. Okay, or if I want to give another example about it, how exactly it works. So let's say I'm standing in front of a mall and people are going, and I have just taken a sample of 100 people who are going to a particular shop to buy something. So if I can simply plot a bar graph of the people, about whatever shopping they have done, it can be a part of descriptive statistics. We are just describing the data. We are doing the plot, the mean, the median, mode, standard deviation. But what if I do some sort of if I deep down if I go to another level, and if I drill down the information, and I come up with that, if I say 75 or 80% of the people are buying shoes, or 10% of the people are going for winter shopping or summer shopping. So those kind of outputs, if I can get from the data, this is where the inferential statistics come into the picture. Okay, so when it comes to descriptive statistics, I have just taken an example of restaurant rating. So whenever we go to Python or R, as soon as we load our data set into a data frame, this is the first thing I think we do. And there are standard libraries available like pandas and numpys, where we can just simply describe our whole data set, how it looks, what are the things are available. And let's say that this particular data set consists of place ID, ratings, what kind of food ratings are there, and the service rating. So what we do, we simply describe the data. Okay, how it looks, what is the count, mean of each and every column, what is the standard deviation, the minimum value, the maximum value, 25%, 50%, and 75%. So obviously, I think most of the terms are very much clear. Everyone knows about mean, standard deviation, the minimum, and the maximum value, and we can directly compare those values. Obviously, we know the data is not scaled. The ranges are different. Here, the minimum value is 1, the maximum value is 2. But here, if you notice, the minimum value itself is 1,32,000, and the maximum value is 1,35,000. So all these kind of basic information we get as soon as we do this job, like the describing of the data. We can do it in Excel also. That will be a manual task. But like the libraries are available, we usually do it in Python and R. Okay, so what is this 25%, 50%, and 75%? So 50% is nothing but the median. So this is the median of our data. This is the middle value of our data. I mean, if you consider this rating column, the middle value is 1. So almost 50% of the data is 50% of the data is staying left side of the mean, the middle value, and the 50% of the data is staying right side of the middle value. And when it comes to this 25% and 75%, so these are nothing but the quartiles. So let's consider this example, how we calculate the quartiles. So just a basic example, we have this data 5, 7, 4, 4, 6, 2, 8. So like the median, whenever you try to find out the median, we have to store the data. Either it will be ascending order or descending order. And this is the similar way we find out the quartiles. So what we used to do, I mean, this is the data set having 7 values. We try to make it into the 4 equal parts. So the first part will be nothing but the first quartile, like the 25% of the data. And then we have the middle part. This is the median. And then we have something called upper quartile, like the Q3. This is about, I mean, this is having the 75% of the data. So if you say, like, there are approximately one data point which is, below 4, or which is having the 25% of quartile, and the middle value is 5. And then you say that there are, exactly one point which is greater than 7, or this is the 75% of the quartile. So this is how we do it in quartile. So as you can see, the 75% of the portion, the 75% of the data set is less than 1, and 75% of the portion of the data is greater than 1, or you can say less than 2. Sorry, my mistake. 75% of the data is greater than 2, or you can say less than 2. So basically, these kind of basic informations we used to get, and this is how we understand the data. So most of the time, nobody gives us the information about the data. So I mean, as a data scientist or as a data analysis, we are the one who have to find out all the information. So I mean, these are the basic procedures we follow. What kind of data, how it is varying, what kind of quartiles it has, minimum values, maximum value, and is there any outliers, and all those stuff we do. So this is the part of the descriptive statistics. I have just taken the example from the Python. You can do it in R as well, and MATLAB also can be done. When it comes to this box whisker plot, this is one of the important step we do. It can be call it as 5-number summary or box whisker plot. So this is nothing but the similar way I have just explained. Okay, yeah. So box whisker plot. What we do as a theoretical, if I want to understand, so this is the middle value will be median, and then we'll be having upper quartile. This is nothing but the 75% value which we were seeing in the previous table. And then we have lower quartile, the 25% of the data, and then we have lower extreme. This is the minimum value, and this is the maximum value. If I go back, this is what I am plotting down over there. The box which are the minimum, the maximum, the 50%, the 25, and the 75%. And with the help of this box whisker plot, we can finding out the outliers also. Is there any anomaly in the data? Is there any outliers? So this is one of the simplest technique to find out the outliers, rather than going for the k-means algorithm or different kind of unsupervised learning to finding out the outliers. Obviously, if we have something, we can do with the basic techniques as well. So what I have done, I have just taken the simple example. There are two different salespersons, like Angela and Carl, and this is the sales of the. They have done. They are working in a company, and the data is having 12 months of their sales data. So what sort of informations we can get from these two different box whisker plot? First of all, we can say the Carl. This guy is having the minimum sale and the maximum sale, which are in both the cases they are higher than the Angela's sales. So if at all this minimum sales is going around 5 or 7, Angela is having way beyond that, like the 0, the minimum one. So those sort of what do you say, informations we can get out from the box whisker plot, like the highest and lowest sale. And if you notice, the median is also higher than this particular box plot. And if you see the interquartile range, so interquartile range is nothing but if you subtract Q3 minus Q1, that will be our interquartile range. That is also higher for this guy, Carl. So we can say, okay, somewhat Carl is better than Angela. He's doing his job in a better way, or maybe he is more productive and he is more efficient. So if we do those sort of basic analysis before going for a complicated and difficult model, those sort of understanding we can get from the data. This is how this box whisker plot is very much interesting, as well as simpler to get the information. How we can do the outlier deduction? So obviously we have this minimum value, this is the maximum value, and then we have Q1, Q3, and then in the median. So Q1 is nothing but, as I have already told, 25 percentile, and the Q3 is 75 percentile. Sorry. So from that we can just finding out the interquartile range. And if I just simply put this formula, Q1 minus 1.5 of interquartile range, then we will get some sort of threshold limit in the left side and the right side. If any data point is staying outside this particular limit, those can be considered as an outlier. So I'll just quickly repeat it once again. So if the data, let's say for example, this minimum value is nothing but the Q1 minus 1.5 of interquartile range and plus 1.5 of interquartile range. If the data is staying outside of these limits, we can consider those things under the outlier or the anomalies present in the data. So if we know those things in advance, we can, obviously we cannot remove those things, but if we know, okay, there are 1 or 2 anomalies which are going above the data and which are having a very higher value, we can take these kind of actions in prior instead of directly putting everything into a model. Obviously it will behave very abnormal. So if you know these kind of informations in prior, that really help us to hyper tune our parameters, so called. So this is how this box whisker helps us in the outlier induction. Okay, so moving on to the next topic called covariance, and we have something called correlation. So I consider both the things, covariance and correlation. So this covariance, whenever we do time series analysis, like AR, ARIMA models, autoregressive models, moving average models. So we usually get these terms called autocovariance, autocorrelations, or let's forget about those things. What is a simple covariance? So this is nothing but it tells us the direction of the linear relationship between two variables. Okay, whether they are positively correlated, whether they are positively related or they are negatively related. And the values can be minus infinity to plus infinity. Because the data is not, the data is not scaled. So these limits they are totally based on the limits of the variance of different variables. So if I considering x and y, so that limit will be differently available for both the variables because the variance are different for different variables. So covariance is nothing but it only tells about the direction. It never tells about the magnitude, how strongly they are correlated. So obviously in the real life cases, the data won't be scaled. There will be a different kind of variations available in different features of our data set. So we cannot apply covariance. It cannot tell us that the correlation between, not correlation, the relationship between the different variables. So this is how, if the covariance is less than 0, it only talks about the direction. The data will be something look like in this way if it is perfectly correlated. And if it is greater than 0, obviously it will be in positively going upward. And if there is nothing, there is no covariance at all, or it is approximately 0, this is how the pattern will be. So this is what the covariance is. It's only talk about the direction. There is no magnitude related to it. But when it comes to correlation, obviously it measures the strength of the relation, how strongly how strongly two variables are correlated with each other. So when we say, obviously it is considering the covariance itself, whatever we have calculated in the last slide, covariance. But what it does, it scales it. It is considering the variance of, standard deviation of variable x and standard deviation of variable y. And it scales the data into +1 and -1. And we know that the data, if the data is towards extremely -1, it will be totally negatively correlated. And if the data is perfectly correlated, that will be the case of +1. And if you have the value 0, there won't be any correlation in between. As you can see, the different graphs I have plotted over here. This is the perfectly scenario where the two data are perfectly correlated. If one is going upward, another is also going upward. Then we have a little less correlated. The data is little separated out, but still they are having a positive direction. They are going upward. In a similar way, we have this perfectly negatively correlated. If I increase x by 1 down, if I increase x by 1 point, y goes down by 1 point. This is how the perfectly negatively correlated data looks like. So those are the things we do. Usually we just we plot a heat map with respect to our output class. We say, okay, how many variables are directly correlated with my output class. Let's say I have a data set of around 30 variables and my output class is having two things. Either it can be yes or it can be no. So my first step is whether all the 30 variables are related to my output class. Because if you go with all the 30 variables, it might go for an overfitting problem, it might go for underfitting problem, and obviously the computational challenges are obviously there. It will take some more time to calculate with 30 variables rather than going for 10 variables, and which are very much important for our problem. So this is where the correlation comes into the picture, and it helps us to do the dimensionality reduction. Obviously, if we can see directly two variables are positively correlated, and we know if one is going up, another is also going up, we can take instead and any one of the variable instead of taking both the things. So this is one of the basic techniques to do the dimensionality reduction rather than going for PCA and other stuff. Obviously, we can do PCA also if you don't know any kind of relationship between the data. So correlation is kind of a very simple technique which tells about what are the variables which are responsible for our output class, and we take only those variables and then feed it into any kind of model, and then we get the output. So just quickly, what is the difference between covariance and correlation? Because they are very similar terms, but still have a minor difference. So as I already told, one is one only tells about the direction, another another talks about the strength and the direction, which direction, whether it's positive or negative, and how strongly they are. And in this case, there is no limit of the the values. It can go to extreme minus and extreme pluses also. But in this case, we have a proper limit. We can we can check different variables. Say I have 10 different variables. I can see, okay, how many are close to 1, how many are close to -1. So those ranges are restricted to -1 and +1, and that's the good part of correlation, because we can compare different variables with each other. We cannot do any kind of comparison here because the limits are different. Say for example, whenever we find out the covariation, the output comes 500. In the next case, it comes 50. But we cannot say, what is the significance of 500 and 50? But in this case, we know, okay, if the data is towards minus, it's negative. If towards plus, it's positive. And whenever the scale changes, obviously the covariance changes. But in this case, there is no dependency with the scale of the data. If one data is having in a scale of 1 to 10, another is having 1 lakh to 2 lakh, obviously there won't be any issues with the correlation because it handles the scaling part. As I talked about in the last slide, like we are dividing with the standard deviation of both the variables. So it removes the scaling issues. But in this case, we always have the scale issue. And obviously the units also. If you have the data into centimeter or kilograms or pounds, obviously the output will be totally dependent on the units. And correlations, we have unitless thing. There is no issue with the unit. It can be pounds, it can be kilograms or anything. So these are the little very minor differences between covariance and correlation, but it's good to know about those things rather than blindly go for the correlation. In some way, obviously covariance is also helpful. In most of the cases, correlation is helpful. As I already mentioned, time series analysis, it's always starts with finding autocovariance, autocorrelation, and all those sorts of keywords are there. So this is the application of these two keywords. Covariance and correlation. And this is one of the simple and might be confusing topic. This moving average, we usually do it in in real life scenarios whenever we receive any sort of data.
Excuse me, sir.
Yes, please.
Yeah, we use a correlation coefficient for goodness of it, right?
Correct.
So what's the difference between correlation coefficient and KS test or chi-square test?
Okay, yeah. So first of all, when you are talk about the chi-square test, so the chi-square we do usually for the sampling method, like we do take out some samples and then we utilize all the outputs in terms of the population methods. And the another good point of chi-square, I'll be covering those concepts also in the later part. But chi-square, first of all, it talks about the categorical data. The best advantage of chi-square is it calculates the dependencies between the categorical data. As soon as whenever you do the correlation with categorical data, you have to do the transformation, because you directly, I mean, the machine does not understand the text when it comes to the categorical data. Okay, so we have to transform the data and then we have to apply the correlation. But whereas the chi-square, it has its own advantages and it works very well with the correlation. I mean, it works very well with the categorical data.
Okay, thank you very much. And what about KS test, Kolmogorov-Smirnov test?
Yeah, so I think I'm not very much sure about this KS test, but when it comes to the correlation part, we usually go for this Pearson correlation coefficient, because this is one of the well-known methods and well-known identified methods. So Pearson correlation coefficient. But
Okay,
KS, I'm not very much sure about it right now.
okay, because I use failure data for reliability studies, and
Okay.
for that we use KS test as well as chi-square as well as correlation coefficient. So there was a confusion which is the best method. So that's why I asked this particular question to you.
Yeah,
Thank
so
you very much.
now I can recollect about this KS test. So whenever we do this kind of, okay, when we do this time series analysis, so it talks about, the stationarity and non-stationarity. So we have something called Dickey-Fuller test, chi-square test, and KS test. So let's say, the data is non-stationary, and that's a part of hypothesis testing, if I'm not wrong. And I'll be covering
Yes, you
that
are
as
right.
well, hypothesis testing and different kind of test. But I think I haven't included the KS one, which you are talking about. But at
Okay.
least you will get an idea about the chi-square, how it works with hypothesis testing, and maybe
Yeah,
other
yeah.
will.
Thank you, sir. Thank you very much. Please continue.
Can,
Thank you very much.
yeah, hello sir, I have one question.
Yes.
Yeah, which transformation will work if we want to apply for this moving average?
Yeah, for moving average, right now we don't need any transformation, because that's what, the moving average does. So if you're talking about the moving average, obviously what we do, we calculate the data I mean, we calculate the average with respect to a window size. In normal average, what we do, we just simply finding out the average and we'll get a single number. But when we talk about this moving average, we take, different window size. Just a minute. So as you can see this box, this window size is totally dependent, or totally, there is no hardcore formula for choosing the window size. It is
Okay.
totally based on our problems. Let's say I'm talking about the process variation, which is very, very fast in the field of predictive maintenance. If one component can be having a very fast variation, like within the milliseconds, another component might be pretty slow in terms of minutes. So it's totally up to us, but how to choose the window size. So when the data is in milliseconds, if you take the more number of data, the data will be more smoothened. I will show that also.
Yeah. Thank
Okay.
you.
So what is moving average? As I have just mentioned, it calculates the average over a period of time, and that is the period of time is called the window size. And we don't know how to calculate the window size. It's totally dependent. It can be a hit and trial method as well. We can try out with the different window size. The best, I mean, whenever we see a best output, we stick to that, because there is no hardcore formula for that. And this is how we're finding out. But if you notice, at any point, any moment of the point, the data into the window will be constant. It's kind of a queue. So as soon as we start from here, let's say our window size is 10. In this case, I have taken the window size of 1 minute. So these are nothing but our indexes with milliseconds. So I have taken window size of 1 minute. Next time when I move this window, one data will come into in and another will pops out. So this is how the window size works. At any moment of time, the window size will be constant. We'll be having 1 minute of data. But whenever I move it to the right, the data will be keep on coming in, one data at a point and the another will go out. Kind of a DQ, first in, first out. So this is how this moving average works. So what I have done is I have plotted two graphs for different window size. So as you can see, the data, it is a real time data of a machine, which recently I was working into one of the problem statements. So the data is varying a lot, and the data is in milliseconds. So if you see the 1 minute of moving average, it is pretty much able to understand the pattern, very much close to the real life, whatever the real time inputs were. In this particular case, it has missed the spike, but most of the time it is capturing all the pattern. So now it's up to us whether we want to conserve this data. It's up to us. Our problem statement, if I go for 2 minutes of the window size, the data is little smoothened. it is not capturing all the spikes. It is going, somewhere in the middle. But if I take a larger window size, let's say 10 minutes, now our most of the data is smoothened, because let's say I have taken the window size from 20K to 40K, 10 minutes, because the data is in milliseconds. So whatever spikes are there, it will calculate the average for it and it will smoothen the data. So, I mean, that's the issues with the window size. We cannot take too much of the window size also, because it will smoothen our data and hardly you are able to get the trend. As you can see, if you only take out this window, I mean, the moving average, the data is constant. You will see there is no trend in it. If you see, you can see some kind of cyclicality, some kind of cycles are happening. But as soon as we go back to this moving average of 1, it can see there are a lot of variation in the data. Maybe this particular portion can be considered as outlier. So what we do usually, so whenever we play around with linear regression or any sort of problems, related to machines data which are having very fast variations. So either what we can do, we can, whenever it comes to the prediction, we can directly feed the data into one of our model, like time series model, LSTM, or linear regression. And what we can do, we can finding out the moving average of our data, and then we try to feed the data. Obviously, whenever you compare both the things, the moving average stands out, and the performance of this moving average input will be better than the normal data. So that's how we do. Whether you take an auto encoder or any kind of algorithms, we always try to put the data in terms of moving average, so that it will be easier for us to predict in advance. So if I say 1 minute, if I go into the bottom, into the extreme right, this is the end of my data, I can, at least I'll be having a 1 minute prior prediction. If I take 10 minutes of the data, I'll be having 10 minutes of prediction, but still the data will be, data won't be capturing the whole variation. So there are bit advantage and disadvantage as well. But again, the choosing the window size is totally up to the person who is working out in the problem. It might, sometimes the 10 window size works for for some person, because the data is based on that particular, granularity. And we are talking about months of data. Obviously, the window size will be in terms of months. So it's totally dependent on the data. So this is what the moving average is. So, but based on my experience, so as I was mentioning, usually we consider moving average nowadays to get the better accuracy in any models. Even you guys can also try it out. You try a linear regression problem with normal actual data, and then you try to find out a moving average. If it is some sort of real-time production data or those kind of stuff, if you have, you try this moving average thing, it will definitely give you better results, because it captures the trend with every window size and one data at a point.
And sir, is there any rule of thumb for selecting the window size?
Apparently no, because as I was telling you, if I consider an airline data set which is having years of data, in that case I will be considering, say for example, 1 month of window size, or 1 week of window size. And the another case, right now in my particular scenario, I was having a machine of, I was having a real-time production data where the process was very fast. The data was in milliseconds. So for me, 1 minute of data is having sufficient information for me to predict. So that's why I chosen 1 minute. So for me, even also, I tried a lot of hit and trial stuff. I tried for 1 minute, half of the minute, 2 minutes, 5 minutes. Then I finally stick into 2 minutes. It has some, it has captured some kind of variation, some kind of spikes as well, so that it will be easier for me to predict. So it is totally based on the problem. There is no thumb rule for that.
Okay. Thank you, sir. Thank you very much.
Okay. Yeah, so moving on to the linear regression. This is one of the most popular algorithms we have, and anyone goes for data science or data analytics, this is the first thing I think we learn, linear regression. And it is, people are practicing it over 200 or 300 years back. And it is still one of the most strongest algorithm present right now.
Hello, sir. I have one question, please.
Yes.
Yeah, you talk about airline data set. So I had worked on that. I have one confusion. When we need to apply the seasonal decomposition, if it is there in the data set.
Okay. So when I was talking about the stationarity and non-stationarity, right?
Yeah, yeah.
So we know obviously the data itself is airlines data. I was talking about festival season, and sometimes, and if you notice in the every weekend, there will be a high number of the passengers traveling, and the price will be higher compared to the weekdays. So this is how the cyclicity happens. Maybe seasonal, we have three kind of variations. One is seasonal, another one is cyclic. Okay, and maybe you have some kind of due also.
Yeah.
So there is a lot of noise is coming from the background. Okay. So in this airlines data set, what we do, so whenever you put anything into a model like LSTM or ARIMA, autoregressive, moving average, we never put everything all together. We always convert our non-stationarity data into stationarity, and we have so many different methods available. It can be hypothesis testing. You can finding out whether the data is stationary or non-stationarity, and then we convert it. Maybe we can take log also. If you take the logarithm, it converts the data into stationarity, but not all the time. Sometimes it works. So we have different technique. So as you are talking about the seasonality variance, what we do first, whenever we feed the data into any kind of model, models for time series, we convert into non-stationarity to stationarity. We do our old calculation, we do the prediction, and then we do the reverse part. We again come back from the stationarity part, we reverse the data, like it comes back to the actual data, like the non-stationarity one, and we get the prediction. It's up to the person who wants to predict whether you want to keep the seasonality variance or not. But eventually you will retain it because you are just transforming it and you are coming back to it. So this is how it works for the time series or the airlines data set.
Thank you, sir. Thank you so much.
Yes. So when it comes to the linear regression, obviously, the task for any person will be to finding out the best line. We have a data across, there will be a lot of data points, and we have to finding out the best fit line. And we expect that all the data point will be staying in the line, but that won't be the the real life. In real life, it is very hard to get everything in the single line. But we want that all the data points should be as close as possible to the data. To the predicted line, whatever you have predicted. So this is the actual target for any person who is working into the linear regression or anywhere. We want to find out the best fit so that it fits our all the data points. And in future, if we do any sort of prediction, at some point of the time, we should have a sufficient amount of prediction available. It can be a sales data, it can be any kind of financial data. Even we do some kind of time series analysis also with respect to it, how it will behave over the time. But obviously in time series, we have a lot of variations. So the simple linear regression won't work out over there. But in sales data and financial data, obviously it is still one of the robust algorithm present. So the idea is to finding out this y, the predictive variables with respect to the slope and the intercept. So this is simple line equation. We have the quadratic equations also, and then we have so and so on. So this is one of the simplest equation. So this is the slope, this is the intercept. So if we have the positive slope, obviously if x increase by one slope, obviously y will also increase by one slope if the slope is 1. If the slope is 2, obviously if you increase x by 1, the y will increase 2 times. So this is how it looks in terms of the mathematical formation. But eventually our target is to finding out the best fit line. And then we finding out the error, what is the actual output, what is the predictive one, and then we scale this the outputs, and then this is the error of our this line. How much we are able to correctly predict and how much we are skipped. So this is the error, and we want to minimize it. It's kind of a optimization problem. Minimize the error, where you have to obtain the best values of these particular weights like M and C. So in optimization, in operational research, this is our common issues. We have to maximize something with respect to get the ideal linear equation, or we have to minimize something. Like in sometimes we want to minimize the cost, we want to maximize the production. But for that, we need to take account all these input variables. Like in this case, we have only 2 variables. In another case, like quadratic equation, we'll be having multiple. But our target is to optimize these values so that we'll get the minimum errors. And that's what the linear regression do.
Sir, I have one question.
Yes.
So what is rank regression on X and rank regression on Y?
Rank regression of X.
Yeah.
So as far
Because
as yeah, please.
Yeah, so what I read that there is y-axis and x-axis, right?
Yes.
So if you want to get more accuracy for x-axis values, Then draw a straight line such that the horizontal distance between the line and the points will be as minimum as possible. That is called as rank regression on X. This is what I have read. And alternative case for the RRY, that is rank regression on Y, that is draw lines such that the vertical distance between the line and the points will be minimum. So can you highlight this one? Thank you.
So yeah, rank, because most of the time we use this terms called rank in matrix operations, as far as I know. But when it comes to these kind of scenarios, I mean, personally, I haven't came across this rank algorithm in the rank linear regression, but I have, included one of the topic called this adjusted R square and R square, where we use the similar concept, whatever you have said. I mean, we draw a horizontal line and we see how much, accurate our algorithm is. Maybe I'll try to cover that, and you can, tell me in that point whether it was something which you are expecting or it is something different.
Sure, sir. Thank you, sir.
Okay, so in linear regression, and then we do this residual analysis. So residual is nothing but the error. And so, like I was talking about, right, the prediction and the actual value. So this is our residue. In sometimes we get this keyword called residual analysis, and this is what we do. We have to check how efficient our algorithm is. So as you can see the plots, these plots we want as close as to this particular line 0, because we want our error to be minimized, and the minimum error is nothing but 0. So we want our all the data points, all the green points should be as close as to 0. If at all they all are lying to 0, it's perfect, no issues, because that's what we are expecting. But in real life scenario, this won't happen. We get some kind of difference, but our still target is to minimize those difference, and we want everything to stick to this particular line, this horizontal line. So this is what we do residual analysis for linear regression. And obviously, if you are noticing that, I mean, those patterns, these pattern doesn't matter, because we are talking about the errors. These are not the real time data. So these patterns does not exhibit any information about it. So you are not, I mean, there is nothing to worry about the pattern. Our target is to get these green dots as close as to these value. I mean, this particular horizontal line, which is, plotted over 0. And if we get the data as close as to 0, if we get the error as close as to 0, the more, better algorithms we get, like the linear regression one. Okay. So when it comes to, we have model 1 linear regression. We go to some problem statement. We have created the linear regression. But now, how you will tell that, say for example, I have created one linear regression model, and all of you guys also created one. But how to compare that mine is better than yours or yours is better than mine? But for classification problems, we can, finding out this accuracy thing. We'll say, okay, my algorithm is more accurate than yours, because there's a way of finding out the accuracy. We can simply create the the confusion matrix. We'll say, okay, total true positive plus 2 negative divided by the total number of predictions, there will be the accuracy. But in these kind of scenarios, like the regression problems, we don't have accuracy. So what we have to do, there are 3 popular metrics available, like R square, mean square error, or the root mean square error, and the mean absolute error. I think every one of you must have heard these terms. They're a little confusing, but I'm sure that after these another 2 or 3 slides, it will be pretty much clear for you. So R square is nothing but, obviously this is the formula, but in simple terms, what happens exactly is, just think about this particular formula. This is nothing but, the actual value minus the predictive. Y cap is nothing but the prediction, whatever prediction we are doing. So this is our equation, the equation of error, actual minus predicted. And then we are doing the square. Why we are doing the square? Because we have to remove the plus and minus sign. Because if the error is more, actual value is less, obviously we will get a minus sign. So that's why we are doing the squaring part, just to remove the direction. In the similar way, what we do, so let's think about this linear regression issue. Yes, this one. So this is what best fit we are finding out. And then what this R square does is, it will simply do the average of all the data. It will simply find out the average, and it will plot it here. Okay. So now just imagine, this is the equation. This is a very simple model, because a linear regression can be an average of all the data points. So this is the simplest model available. Just simply the average. This is called sum squared. And this is our linear regression, whatever we have predicted. So just imagine, This is numerator, this is denominator. If the error, whatever the algorithm we have done, the linear regression, if error are very, very less, if if our model is very much accurate, and if these errors are less and these are very high, obviously we will receive a very less value. If you divide a higher, if you divide a lower denominator, sorry, if you divide a lower, higher numerator with higher denominator, you will get a less value, and the data will be close to 1. And that's what it indicates. If R square is very close to 1, it is, the model is more accurate, the model is better, the model is more efficient. In the other terms, let's say our model, whatever we have developed, is behaving very badly, it has very, very high errors, and the simplest model available in the world for this particular data, that is with respect to mean, is better than this model. Obviously this value will be lesser and this one will be higher. If you divide these values, we will get a higher value, and the data will be more towards 0. So that's the, that's how this R square calculate. And we say that the value will be, will lie between 0 to 1. And one will be the more robust model. So in our case, I was talking about, right, how to compare your model with my model. If I say my R square is very much close to 1, and if your R square is, far away from my value, obviously I can say I have some values, or I have some concrete proof that my model is better than yours. That's what, because we cannot simply try linear regression everywhere. We have different regression issues, and we have to try out different things, and whichever outperforms with the many algorithms, you have to take that, because there is no restrictions of use of linear regression. So obviously this is how this R square works. It initially took, for me also it took some time, but now it's pretty clear. You have to just simply plot the basic model with respect to mean, and this is the prediction value, the best line of fit you are getting. Just divide these things, subtract it from 1, you will get some value. This is how the R square is getting calculated. And then obviously if the model is overfit, right, overfit conditions, so the model try to learn all the patterns, all the different patterns. So this is how this overfitting happens. So overfitting, what it does is, R square does not consider this overfitting, because it will simply say, okay, the error is very, very less. Okay, the model will be more closer to 1, and that's why it is more efficient. But in case of overfitting, we cannot say our model is overfit. So in that case, this adjustive R square works. It basically, penalize the data, and it removes these issues, these overfitting issues. So this penalizes nothing but, this K value. These are the number of independent values the model by itself added, and we calculate the R square adjusted, or adjusted R square. And in the end, if we say adjusted R square and R square, if they both are similar, then we can say, obviously, the model is not prone to overfitting, and it is very robust. So whenever you try out any linear regression model, first always calculate R square, then calculate R square adjusted, then see what's the difference you're getting. If you're getting a huge difference, then you can consider that, okay, your model is overfit. You need to hypertune your parameters. Otherwise, if both the models are having very similar values, then you can say, yeah, everything is good. We are not overfitting our model, and our model is robust enough, and it can go to production. So that's what this R square does. And mean square error is pretty simple. I was earlier talking about the sum square. This is the actual value, this is the predictive value. You have to just square it and divide it by the number of samples. So it is nothing but the average of errors, and that's what the name is, mean square error. But what is the issue with mean square error? Because we are not doing any kind of scaling. The values can be in thousands, or it can be in the numbers can be very big, so we cannot interpret it. Say, for example, my model has some 20,000 of data, 20,000 of error value, and another model is having 50,000 of error value, and in sometimes it will be very big. So that's the issue with the interpretation when it comes to the mean square error or root mean square error. So then what it does is, we do this mean absolute error. So in that case, what we do, okay, let's imagine in this case, in some point of the time, there was a big difference between our actual value and the predictive value, and you do the square. So if you do the square of, say, for example, 20, it will increase to 400. Or if you square another big value called 2000 or 2500, it will square it, and it will be a very big number. So in this case, this MSE is having some sort of issues when it comes to the squaring part. So what another matrix does is, it simply do the absolute part. It is not doing the squaring. It is considering each and everything parallelly, and there is no weightage to anything. So it is simply saying, okay, if the error is high, keep it same. Just remove the sign. Just keep it absolute, and then just do this. Just take the average out. So that's how this MAE calculates. So it is nothing but the absolute error, and this is kind of better than the MSE. But in normal scenarios, what we do is simply calculate everything. We calculate R square, we calculate MSE, and we calculate MAE, the absolute error, square error, and R square. And then we see, okay, how efficient our model is. This matrix is somewhat, really important to understand at least what those numbers are coming. Anyway, there are all predefined packages available in Python or R or any sort of programming language, but we should understand how these values are coming out. What is the math behind it? And obviously, I have just explained which one is better. Obviously, this R square helps us to explain our model. Say, for example, the value of R square is 0.79. So we can say 79% of the dependent variable is explained. At least the regression model, whatever we have created, 79% or just imagine 99% of the data is already explained, because eventually our target is to capture all the variance whatever we have in the input variable. So that's what it can, I mean, it is just kind of a, for the better way of explaining it, we use this R square, and then we have this MSC and MAE also, just to compare the performance between different regression models. And then I was just talking about this overfitting and underfitting. These are little confusing topics, but still I'll try to just quickly tell you how it looks when the model is overfitted. And this is a pretty common scenario. This happens every time. So this is our good fit robust model. This is how we are expecting that if we have some kind of variation or some kind of trend in the data, our line should fit into the data. But even though we are not expecting that, our line should fit each and every data. As you can see, the line is fitting each and every data point. Okay. And in this case, the model is very simple. Like I was talking about the average model. It is not at all capturing any kind of variation. So this is called underfitting. So underfitting is whenever we do any sort of modeling, we do training and we do the testing part. We split our data set into training and testing. So underfitting is nothing but whenever you see a high training score as well as the high testing score, it means there is an issue that you are not able to capture all the information and your linear regression model has some issues. That's why the model is underfitted, because it is not, good enough. But when it comes to overfitting, your training error will be very, very less. But when it comes to the testing data, because as per the standard practice, we do our training, we calculate, we create our model based on the training data, and then we test it on the tested data. So the model will behave very nicely on the training data because it has understood all the patterns of the data. But when it comes to the new bunch of data like the testing one, it is behave very badly. So whenever you see a big difference into a testing score and training score, definitely it's a case of overfitting. You can just simply note it down. Just finding out the R square, mean square error or mean absolute error for your training data, and do the similar for the testing data also. If you see a huge difference, if your training score is very high, or maybe if your training score is very, very less, but the testing score is very high, obviously it's an overfitting model. It will behave very nicely with that particular set of data, but whenever you give any kind of new data set, it will behave very, very badly. So this is how this overfitting problems happens. And linear regression has really issues with overfitting. That's why we have something called ridge regression and lasso regression. So if you notice, most of the things remain same, but we penalize our weights. So whenever we see the model is understanding each and everything, it penalizes the values of the weights, and we choose the lambda value according to that. So the more the high, there will be lesser error, it will increase the value of lambda, and if there is a higher value of error, it will reduce the lambda. So that's how it does. But obviously there are two different topics which obviously take a good amount of efforts to understand. That's why I'll just simply include those things. But just remember, whenever we have overfitting issues like the training and testing errors, just try out ridge regression and lasso regression for your problems. Maybe your model will be having better results. Okay, yeah. So I think, yeah, we have around another 10 or 15 minutes. So I'll quickly consider this hypothesis testing as well. And this is really one of the important topic. We see each and every day this hypothesis testing has been used in data science. And what exactly it does is, so we take some kind of guess, but that guess will be kind of a educated guess. We cannot randomly say, okay, who will win today. But say if based on the prior experience, we say today, say India and Australia is playing, and based on the prior experience or all these players' fitness, and if we know everything, we do some kind of calculated guess. Okay, there are higher chance of India will win the test match or Australia will win the test match. But rather than doing the random guess, okay, just choose India and Australia, we'll simply say India. But we don't have any prior knowledge. So this is how this hypothesis testing works. It basically takes an educated guess. So we take a guess, we have to do some sort of calculation behind it, and then we have to see whether whatever we have assumed is correct or not, whether we have to reject it or we have to accept it. So this is how the null hypothesis and alternative hypothesis works. So null hypothesis is nothing but we have to just take a guess. Say for example, there are two different groups, and I will say the two groups are having common mean. The mean is similar for two groups. So for example, mean of first group and mean of second group, they are both similar. This is what our null hypothesis means. And eventually in the alternate hypothesis, what I will say, no, those two means are different. Just take about two different kind of groups. Say for example, say CSC department and EC department, or any one of the department. So let's say the mean average of CSC department is equals to mean average of EC department. This is my null hypothesis. Alternative, what will be? There are three cases. Either they are not equal, either less than, EC is having less average than CSC, and the vice versa. So this is how we formulate our problem. There will be a null hypothesis, there will be alternate hypothesis. Obviously, they are mutually exclusive statements. They both cannot be true altogether. There will be only one thing which will be true. So now we have done our hypothesis. We have created the problem statement, like, okay, now we have to kind of do the calculation, and then we have to say based on the fact that, okay, which one to accept or which one to reject, whether A's are similar or A's are different. So this is how we will calculate it. I will tell you now. We have two kind of tests. One is one-tailed test, another one is two-tailed test. So say for example, when we consider the mean average is greater than or less than, we consider this one-tail or two-tail test. And whenever we say they are both are not equal, we say we consider this two-tail test. So this is kind of the red is nothing but the kind of danger zone. Whenever our data point, our results will lie in between this particular critical region, we have to reject our null hypothesis. So null hypothesis is nothing but the mean are equal. So if you say the data point is coming in this red zone, we have to reject it, because eventually this is our goal. Either we have to reject it, accept this one, or accept this one, reject this one. This is our ultimate goal of hypothesis testing. And you can take any sort of example. Say for example, in a production unit, chocolate bar of they are producing the chocolates, and the chocolate weight is 5 gram. But a quality manager comes and he say, no, the weight is somewhere 5.1 gram or 5.2 grams, so we cannot consider it. What they will do as a quality department, they will do this hypothesis portion. What they will do, okay, let's run out this test. Our ideal size is 5 gram, but no, someone is claiming that no, size is not equals to 5 gram. Now we have the null hypothesis, we have alternate hypothesis. Eventually we have to say with respect to all the tests, which one is better, which one to accept, whether really our chocolate gram, the chocolate size is 5 gram, or it is less than that. So eventually this is our target, whether it has to accept it or reject it. And yes, just I have taken another example. Let's say you are looking for an apartment to rent it, and your budget is 50,000, but you cannot go beyond that. So I was talking about this critical regions. So whenever you say whenever some broker contacted you, or they will say, sir, there is a apartment available, but the cost is 20,000. So simply say, no, I cannot consider it, because my null hypothesis is I will simply consider all the houses which is less than 15,000, and whosoever is greater than 15,000, I won't consider them. So these greater than 50,000 is my critical region. Say for example, this is my critical region. So whenever some broker contact me and the price stays above the 15,000, it means in this particular critical region, I will reject it. I will say, no, I cannot buy it, or I cannot rent it, because this is out of my budget. So this is how we do the formation of null hypothesis, alternative hypothesis. This is how the critical regions can be formed. These are very simple examples. When it comes to the mathematical portions, we have something called p-value. So p-value is nothing but the critical region. So whenever we see any data point is beyond the p-value inside the critical region, we have to reject our null hypothesis. Otherwise, we have to accept it. So what we can see is lower the p-value. Lower the p-value means we have very less chance of accepting the null hypothesis, because we have strong evidence that the alternative hypothesis is true. So that's why low p-value simply indicates that we have to reject the null hypothesis, and if we see high value, we have to accept it. So if at all you are not able to understand the concept, you can simply say in each and every hypothesis test, we have to finding out this p-value and t-test, chi-square test, and whatever you see, ANOVA and all those things. Eventually, we have to finding out the p-value. And if you say high p-value, just remember that we have to accept it. Low value means we have to reject it. And then we have some sort of errors, because obviously we cannot say every time we have to accept it. Like the confusion matrix, we expect that our outputs will be true positive or true negative, but still there will be some kind of false positive and false negative. And this is how this error comes out. We expect that whenever null hypothesis is true, we have to accept it, but sometimes we do the mistake. Whenever it needs to accept it, we are rejecting it, because it's just a phenomena. And whenever the alternative hypothesis we need to accept it, we are rejecting it. So those sort of errors are there, type 1 and type 2. We call it alpha error and beta error, and we consider this level of significance. So whenever we see our calculation is supporting 95% of the confidence interval, we are say, okay, we are confident enough to reject it or accept it. And after that, okay, this is how we do it. First of all, let's see the summary. First of all, we have to formulate the null and alternate hypothesis. We have done that. Then based on the data and probability distribution, we have to select the hypothesis test. Okay, which one need to perform? It can be ANOVA, it can be chi-square, it can be t-test, it can be f-test, it can be A by B test. There are multiple things available. So first, null and alternate hypothesis has been done. We have formulated those things. Our test also identified. We are going to say, for example, we are going to test for the ANOVA. And then this is our level of significance, 0.05 means 95% of the value. Then we'll calculate the test statistics, we'll calculate the p-value, and based on the p-value, we will either reject it or we will accept the null hypothesis. I mean, that's the overall bottom line of our hypothesis testing. This is how we do it. And then we have different sorts of tests available, like ANOVA, chi-square, t-test, f-test. So again, which one to choose? There is no simple formula for that. Okay, this is, if you have production data available, simply go for chi-square. No, we have to understand the data first, what kind of data it is, and then only we can choose the test available. Say for example, ANOVA. ANOVA is simply analysis of variance. But whenever we are talking about a group of whenever the group size is more than 2, we always calculate ANOVA, because we cannot calculate the variance. Because for variance, we need only 2 groups, X and Y. But ANOVA obviously calculate the variance when the group size is more than 2. Okay, just think about a simple example. Let's say a company wants to check out the productivity of an employee. Say for example, productivity of 3 employees with respect to their working hours. So now we have to talk about 3 different employees. Obviously, the group size is more than 2. We are considering this ANOVA. But one way ANOVA is we are only considering based on the working hours. It will be one way. Say they are talking about in terms of working hour and in terms of the break they are taking, lunch break or any sort of tea break. Then we have 2 factors, 2 dependent variables. Then it will be 2-way ANOVA. And if they are considering n number of things, their timings and their break timings and what do you say, there are holidays, how many leaves they are taking, and based on that, if they are checking out the productivity, then we consider n-way ANOVA. So if we know each and every test, I mean how at least they work, then based on the problem statement available in our hand, we will calculate the test statistics for that particular hypothesis testing. And someone was asking about the chi-square. I mean, obviously, chi-square, we have 2 types of tests. One is goodness of fit, and another one is for test of independence. If you are going to check how 2 variables are, related to each other, then we calculate this chi-square test also. I mean, we can do the correlation as well, but we can do the chi-square also. And if you get a small value of psi square, obviously there will be a relationship present in two variables. Just remember that. I mean, if at all some kind of confusion in understanding the concept, if we have a higher value of psi square, there is no relationship between two variables. If there is a small value of psi square, it means there is a relationship. And when it comes to t-test and f-test, obviously we always talk about two group size. Whenever we have a group size more than 2, we talk about ANOVA. We will always consider this ANOVA. If whenever we have two group size, we go for t-test and f-test. Simple as that. So f-test is nothing but it calculates the, I mean, whenever you have two groups like S1 and S2, it calculates the variance for S1 and S2. And if say, if both the variants are equal, obviously S1 is equals to S2, the f size will be 1, and that will be the ideal scenario. But in most of the time, we will see sometimes S1 will be lesser than S2. It's just simply the numerator and denominator stuff. If S2 is greater than, obviously we will get a less value of f-test. If S2 is lesser than, we will get a higher value of f-test. So these are nothing but the test statistics of different kind of problems we get for hypothesis testing. But eventually, this is how we work. There are the 7 steps. We have to formulate the null and alternate hypothesis, identify the correct test to be performed, calculate the standard value, test statistic, type p value, and then eventually this is the most important part. Either we have to reject it or either we have to fail to reject it. So if you take the example of our chocolate bar, say we have already formulated null and alternate hypothesis, and then we have for chocolate bar, obviously we are talking about we can go for t-test also and f-test also, and then this is our level of significance. Eventually, if we say no, we have strong evidence that our chocolate size is 5 gram only, we will simply say okay, accepted, because we have a concrete proof behind it, and this is how it works. So we can use this hypothesis testing in any sort of equations, anywhere. Whenever you get any kind of problem statement, you can go for that. So yeah, given that, yeah, if we have time, I can quickly talk about this quality controls also. Like I mean, in most of the quality controls or quality departments, we use this Lean Six Sigma methods or the statistical process or quality controls. And this will be the last topic for the today's talk. Yeah, so what we do is in statistical process quality control, we measure and we analyze the the process variation, and we calculate the upper limit and lower limit, and this is the central value. And there will be the real-time data will be keep on coming. Our target is to finding out the upper limit and lower limit. If something is going above the line, we can say, okay, this is some kind of outliers or abnormality into the data. Or if some data is going beyond this lower limit, obviously we can say, okay, some abnormality is happening. So for one point is fine, but if the data is continuously going beyond the lower limit, someone has to take some action. When it comes to the real-time production data, if the data is continuously going down, it might be because of some machine is down or some issue is happening. So the operator has to take some actions, because our ideal scenario is the data should restrict to the center line. Or if at all some kind of variation is there, it should behave or it should stay inside the upper limit and lower limit. So we have different sorts of charts available, like X bar and range chart. X bar is nothing but the mean chart. So with respect to mean and range, we calculate this upper limit and lower limit. And then we have something called X bar and variation chart. And then NP and P chart. These are proportional chart. Whenever we have categorical data or the quality data, then we consider these charts. And this is one of the decision tree available. You can, if you are confused how to choose the particular chart for my problem statement, just simply say what kind of data do you have. It is continuous or discrete. If it is continuous, check the number of size. We have different size available. If say for example our sample size is more than 10, simply go for X bar, or X bar and standard deviation chart. Similarly, if the data is discrete, if we have some kind of defect available, then you have to simply drill down the data, the tree, and eventually we'll get what kind of chart to be used. And if you know the chart, obviously you will get the upper limit and lower limit, and then it can be deployed into real time. As soon as you get the upper limit and lower limit, whenever the data goes upside of the lower limit or below the lower limit, you have to raise an alarm. So for example, this is the problem statement you receive, that whenever the data or whenever I see abnormality into my data, please raise an alarm or alert the operator. So this is one of the simple techniques to be done. I mean, you can just simply say, if my data is going above the upper control or lower limit, I will raise an alarm, because this is not the normal behavior. So this is about the statistical process quality, just an overview. There are a lot of things to be discussed, but I don't think so we have much time. So if you have any questions, please go ahead.
Sir, I have one question.
Yeah.
Correlation coefficient and R square, both are same or different?
Yeah, correlation coefficient and R square, no, they are pretty different.
Yeah.
Because in
Uh,
correlation, when we see, we are finding out a covariance and we are dividing it with a standard deviation of two variables, like standard deviation of
right.
x and y, because we need to scale the data. But whereas this R square, we are only talking about in terms of error. If you
Yeah.
notice, if I go back to the slide,
Observed and predicted, that difference we are taking, right?
correct. We are only talking about the errors. We are not talking about the real data. But in covariance or
Exactly.
correlation, we always finding out with respect to the actual data.
Okay. The test, the KS test I was talking about,
Mhm.
it is similar to the R square test. So now it's clear
Okay.
to me, the
Okay.
correlation coefficient and R square.
Correct. So even the KS test can be used in hypothesis testing also, whether to reject
Yeah,
it or
right.
accept it. Obviously, we can use it for hypothesis also.
Yes, yes, right, sir. Thank you, sir. Thank you very much.
Most welcome. So, no other
Participants,
questions?
if you have any doubts, please unmute yourself and you can ask your doubts.
I'll wait for another 1 minute, and then if at all there is no questions, I have put my email ID and my numbers. If at all someone gets later on, I mean, I can reply whenever I get a time. I will get, I get some time. So please feel free to note it down.
It's really a great session, sir. We got very, very useful information. I had very much, so many doubts between different goodness of fit tests. So today it is clear to me. So thank you very much, sir.
Thanks, Rajkumar. It's a pleasure. Yeah, so the main target was to cover many topics. I mean, I would have taken a single topic and just to deep down into the particular, say, for example, linear regression, but that will be very specific to someone who is really wanted to work into linear regression. But like, whenever you go for computer vision or text analytics or audio processing, video processing, so these are the common topics we have to utilize. So that's why the target was to give you an overview about all the things, and maybe it can help you for the other 3 days also.
Yeah, sure, sir. Thank you, sir.
What do you suggest? What kind of model we are using for the computer vision?
Yeah, so for computer vision, there are multiple things available. Like we have something called CNN, computational neural network, and we have RNN, recurrent neural network. We have LSTMs also. So that again depends. You can try out the RNN, CNN, and LSTM. Nowadays, obviously, LSTM behaves pretty nicely because it has some kind of the name itself is having long short-term memory, so it retains some kind of previous values and then it do the prediction. So we mainly try out with CNN, RNN, and then it's about LSTM. And in computer vision, we most of the time we go for the classification task. Okay, this and that. Either you capture the retina or whether you are capturing it. Or, I mean, capture the retina or not. Like if the image is having dog or cat, no, yes or no. So we majorly have classification problems. So we can go for RNN, CNN, and LSTM. And in Python, we have a very famous library called, the CV2. I mean, we call it computer vision library only. So I think most
OpenCV.
algorithms are pre-built over there.
Any more doubts, participants? Sir, I think no more questions, sir.
Okay, then I think I'll take a leave now. Thank you guys. Thanks for bearing me. Thank you so much.
Thank you, Deepak, for
Thank you very much, sir.
spending your valuable time here. Thanks a lot, Deepak, for joining.
Okay. Thank you.
Thank you, sir. Thank you for your wonderful session, sir. Thank you for accepting our invitation first and delivering this lecture. Thank you so much.
Thank you. Have a good day. Bye bye.
Participants, next session will be start at